Something truly extraordinary is happening on Mars. In Jezero Crater, NASA's Perseverance rover is excavating what may be the red planet's oldest memories. Within sedimentary rock layers that are billions of years old, scientists have discovered something never seen before. They found tiny circular mineral structures measuring only about 0.2 to 1 millimeter in diameter and named them leopard spots and poppy seeds. Spectral analysis shows that the cores and outer rims of these structures have clear chemical differences, a process strikingly similar to iron ring reactions known from ancient microbial environments on Earth. Hello everyone, I'm Yun Xian. Could these be the first biological traces, faint evidence that life once existed on Mars? Long ago, this planet possessed a thick atmosphere, flowing liquid water, and conditions capable of sustaining life. Get ready, because this discovery by Perseverance may change everything we know about life in the universe. The discovery was made at the head of the Siava Falls, part of the Bright Angel Formation, an area once covered by the Neretva Vallis River billions of years ago. Data returned by Perseverance has finally revealed the first traces within these ancient rocks, two strange microscopic structures, leopard spots and poppy seeds. These are not ordinary natural formations, but ordered structures containing complex chemical signatures. While scanning the surface of Siava Falls, Perseverance recorded a large number of leopard-patterned circular markings, each only about 0.2 to 1 millimeter across. Under the microscope, these leopard spots display an unusually organized chemical distribution. Iron, phosphorus, and organic carbon compounds are highly concentrated in their cores. These three elements are fundamental building blocks of life on Earth, involved in the formation of nucleic acids, proteins, and cellular energy reactions. Phosphorus is especially critical in biology. It is a core component of DNA, RNA, and ATP, the energy currency of all living organisms. This clear concentric structure formed by phosphorus, carbon, and iron forced NASA scientists to pause their conventional reasoning. On Earth, ancient microorganisms often accumulated minerals around their cells during metabolism, forming life signatures known as biosignatures. Similar structures can result from this process, but without life, could purely inorganic chemical reactions under special pressure and temperature conditions produce similar shapes and compositions? What truly shocked the scientific community was the second discovery, the poppy seeds found in rock samples from the same area. Perseverance recorded hundreds of pin-sized spherical mineral grains with structures that defy explanation by conventional physical processes. Analysis shows that each poppy seed has a distinct core and outer layer. The core contains low-oxidation iron titanium, while the outer layer is rich in highly oxidized iron titanium. On Earth, this phenomenon has only been observed during biological iron reduction processes. Anaerobic microbes use iron minerals to generate energy, leaving behind structures with different iron oxidation states. The poppy seeds on Mars almost perfectly replicate this pattern. Could this be evidence of an ancient microbial ecosystem, or merely an unknown abiotic chemical phenomenon? Scientists compared Martian rock samples with Earth's oldest geological layers, particularly those in Greenland and Australia's Pilbara region, which preserve the oldest known microbial fossils on Earth, dating back more than 3.4 billion years. The results were astonishing. Martian samples showed striking similarities in morphology, core structure, and iron reduction traces. This suggests that conditions in Jezero Crater once were remarkably similar to early Earth, sufficient to support basic life processes. Further analysis using the SuperCam spectrometer revealed clay and carbonate minerals. These compounds can only form in environments with neutral liquid water, ideal conditions for life to develop and be preserved. Atmospheric data indicates that billions of years ago, Mars had a much thicker, carbon dioxide-rich atmosphere capable of maintaining stable temperatures. But as the possibility of life grows stronger, a question arises. If life once existed, what caused its disappearance? ESA's Mars Express and NASA's Mars Reconnaissance Orbiter have detected signs of liquid brines beneath polar ice, along with episodic methane signals potentially linked to biological activity. This strengthens related hypotheses. On Earth, methane is often a byproduct of anaerobic microbial activity. So, is Martian methane geological or biological? Even if leopard spots and poppy seeds ultimately proven unrelated to life, they would still represent evidence of unknown geochemical processes, opening new doors in planetary material science. After Perseverance discovered leopard spots and poppy seeds in the rocks of Siava Falls, scientists realized the key question was this: if these are biological remnants, where did they originate? Based on the collected data, the answer is becoming increasingly clear, right where Perseverance is now, Jezero Crater, a place regarded as a time machine of Mars. Jezero is not just a massive impact crater on Mars, but also an ancient lake approximately 45 kilometers in diameter. It was once fed by river systems flowing in from the northwest. Images captured from orbit by the Mars Reconnaissance Orbiter clearly reveal fan-shaped river delta formations. These structures can only form through the long-term flow of liquid water. This delta is the strongest hydrological evidence that Mars once had a stable water cycle, which is a fundamental requirement for life. These rivers brought not only water, but also minerals, carbon, phosphorus, and other elements essential to life. According to NASA's 2023 climate models, the long-term existence of Jezero Crater would have required an atmosphere at least 100 times denser than today's, sufficient to maintain pressure for liquid water. This suggests that more than 3.5 billion years ago, during the Noachian-Hesperian transition, Mars may not have been cold and barren, but a blue planet with clouds, rain, and flowing rivers. As these rivers flowed into Jezero, they deposited sediments rich in clay and carbonate minerals. Both are considered crucial for preserving life. Clay can only form in neutral water environments, making it ideal for prebiotic chemical reactions. On Earth, scientists have discovered amino acids and simple organic compounds preserved for millions of years within clay minerals. Could Jezero be quietly preserving a similar story? A story that has lasted for billions of years? In addition to clay, carbonate minerals in Jezero play an equally important role. Carbonate belts found along the ancient lake's shoreline are seen as evidence of chemical interaction between liquid water and a dense carbon dioxide atmosphere. On Earth, carbonate rocks are often cradles of microbial life. Stromatolites formed by cyanobacteria emerged in such environments. Although scientists have not yet confirmed similar structures in Jezero, a 2024 report in Science Advances revealed complex organic molecules within these carbonate samples. Spectral analysis by Perseverance's robotic arm detected organic fluorescence at multiple sites within carbonate rocks and clay-rich sediments. The evidence of aromatic ring compounds indicates that carbon chains once participated in high-energy chemical reactions, possibly linked to biological or prebiotic energy sources. Yet the question remains, are these traces of extinct life or merely the result of natural chemical reactions occurring under meters of sediment over immense timescales? Oxygen isotope analysis of rocks collected by the rover shows that Jezero's water originated from melting ice in nearby highlands and underwent evaporation-condensation cycles similar to Earth's climate system. This was not a temporary lake formed by impacts or acid rain, but a long-lived aquatic ecosystem. If life once existed, this environment could have allowed it to thrive, evolve, and eventually disappear. If Jezero Crater represents a relic of a once water-filled world, then the next question is, what enabled this now dry, dusty planet to sustain life in the first place? During the Noachian era, between 4.5 and 3.5 billion years ago, Mars was vastly different from today. Beneath an atmosphere dominated by carbon dioxide, tens of times denser than today's, Mars's northern hemisphere may have been covered by a vast ocean, along with river systems, lakes, and frequent rainfall.
Orbital topographic data reveal ancient river valleys, eroded cliffs, and layered clay deposits, undeniable evidence that liquid water once flowed on the surface. Yet scientists are puzzled not only by the presence of water, but how Mars maintained liquid water when the Sun was 30% weaker than today. Carbon dioxide's greenhouse effect may have helped, but recent climate models suggest CO2 alone was insufficient. A new hypothesis proposes that ancient Mars's atmosphere also contained methane and hydrogen. These powerful greenhouse gases could have worked together, forming a thermal blanket that trapped heat for millions of years. When water reacts with volcanic basalt, it releases hydrogen and minerals like olivine and serpentine. This process not only alters the surface, but generates chemical energy, the same type used by early Earth microbes living in darkness without sunlight. Many astrobiologists believe that if life arose on Mars, it likely began through iron or sulfur reduction.
Similar to life near Earth's deep-sea hydrothermal vents. But life requires more than water and energy. Analyses by NASA's Curiosity and Perseverance rovers confirm the presence of all 6 essential elements for life on Mars: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements exist in the form of carbonates, sulfates, phosphates, and nitrates. Carbonates show CO2 once dissolved in water. Phosphates are vital for cell membranes and ATP. Sulfates provide chemical energy for sulfur-reducing microbes. Nitrates supply nitrogen for amino acids and DNA. On Earth, this exact combination, along with suitable temperatures and chemical energy, marks the emergence of ancient life. Such conditions may not have been limited to Jezero alone, but widespread across Mars. Hundreds of clay and carbonate deposits discovered globally indicate repeated cycles of wet and dry climates. These cycles provided ideal environments for natural chemistry to gradually form complex organic molecules. And chemistry isn't the whole story. Recent geochemical models from MIT and NASA suggest that weaker ultraviolet radiation from the young sun may have helped Mars's atmosphere synthesize formaldehyde and amino acids, similar to prebiotic reactions on early Earth. Could life have emerged simultaneously on both planets, only for one to later be destroyed? As probes begin to uncover complex organic chemical traces buried in rocks for billions of years, this question becomes increasingly profound. In Jezero Crater, Perseverance detected rocks rich in carbon and hydrogen. Some of these rocks are partially oxidized and embedded within clay-rich sediments. Spectral analysis shows clear chemical differences between their cores and outer layers, a phenomenon that may be linked to ancient microbial activity. No one dares to claim this as proof of life, but no one can completely rule out the possibility either. Then, Mars began to change. As the planet's core cooled, its global magnetic field disappeared. Without magnetic protection, the solar wind gradually stripped away Mars's atmosphere, leaving behind a barren world. Water evaporated, the atmosphere thinned, and if methane was once produced by microbes, it too escaped into space. Over hundreds of millions of years, a once blue planet turned into a red desert. But perhaps not everything disappeared. Beneath the surface, temperatures remain relatively stable and ice may still exist. If life once existed, it may have retreated underground. Some scientists believe ancient lava tubes, subsurface ice, or deep briny reservoirs could be the last refuges of microbial life, shielding it from deadly solar radiation. Laboratory experiments show that many extremophiles on Earth, such as Deinococcus radiodurans and methanogens, can survive for thousands of years under Martian conditions. Evidence from Jezero Crater indicates that ancient Mars once had rivers, lakes, and stable chemical environments capable of sustaining life. Now, humanity stands at a critical threshold. For the first time in history, the idea of planetary migration is no longer pure imagination, yet as we move closer to answers, scientists have become more cautious than ever. They understand that even a single wrong conclusion could repeat past mistakes and mislead humanity once again. This scientific caution comes from experience. There was a time when the world believed life had been found, only to face disappointment. In 1976, NASA's Viking landers touched down on Mars and conducted labeled release experiments. When Martian soil samples released carbon dioxide gas, the world erupted in excitement. It seemed like the first signal of microbial metabolism. But years later, scientists discovered this reaction was a chemical illusion. Martian soil contains perchlorates, powerful oxidizing compounds capable of mimicking biological reactions without involving life. 20 years later, in 1996, scientists discovered the meteorite ALH 840001 in Antarctica. Inside were nanoscale structures resembling ancient bacteria, possibly fragments that reached Earth from Mars. The discovery shocked the world. But as analytical techniques improved, researchers realized these structures were the result of inorganic mineral deposition, not biological processes. These two events forever changed planetary science, shifting it from optimism and belief to extreme caution. NASA later adopted an unshakable principle: extraordinary claims require extraordinary evidence. This led to the creation of a life detection confidence scale, a 7-level verification system regarded as an ethical safeguard in planetary science. It requires scientists to proceed step by step, like deciphering an ancient code written on Mars's surface. At present, samples collected by Perseverance from the Siava Falls region of the Neretva-Vallis Basin are classified between levels 2 and 3, the hypothesis stage. Is this red planet truly lifeless, or does something lie hidden beneath its frozen crust? As humanity enters the 21st century, new data returned by orbiters and rovers begin to paint a startling picture. Life on Mars may never have truly vanished. It may only be hiding, waiting to be discovered. In 2018, radar signals from ESA's Mars Express stunned scientists. Beneath the southern polar cap, radar detected unusually strong reflections similar to those produced by liquid water beneath Earth's glaciers. After years of analysis, scientists confirmed the presence of a briny water region located 1.5 kilometers underground and extending roughly 20 kilometers. Due to high concentrations of perchlorates, this water remains liquid even at temperatures as low as -70 degrees Celsius. This became the first solid evidence that Mars is not entirely dry. But water alone is not enough. What is happening beneath the ice? Scientists believe in this dark, cold, highly saline environment, organisms similar to Earth's halophiles they exist. These microbes survive in Antarctic salt lakes and can revive after thousands of years of freezing with just a drop of meltwater. If life once existed on Mars, this may be its final refuge, hidden beneath thick ice where time seems frozen. Another clue comes from Mars's thin atmosphere. Methane, a gas rapidly destroyed by ultraviolet radiation, appears seasonally, rising sharply in summer and nearly vanishing in winter. This behavior closely resembles biologically produced methane on Earth, yet the data is inconsistent. Methane is not always detected in the same locations or at the same times, deepening the mystery. It may originate from subsurface gas reservoirs, chemical reactions between water and bedrock, or microscopic microbial activity. Mars's surface environment is extremely harsh. The average temperature is -63 degrees Celsius. Cosmic radiation is intense, and atmospheric pressure is only 0.6% of Earth's. Any liquid water would evaporate instantly. So if life exists, where could it hide? Collapse pits in the Tharsis and Elysium regions are believed to be entrances to underground cave systems stretching for tens of kilometers. At such depths, temperatures remain stable,
Radiation levels drop by hundreds of times, and ancient geothermal heat may persist. On Earth, similar environments, from Icelandic ice caves to deep rock fractures beneath the Atacama Desert, are havens for extremophiles. These organisms require no sunlight, surviving solely on chemical energy generated by reactions between water and minerals. Many scientists now believe Martian soil itself may contain enough chemical energy to sustain microbial life. When cosmic radiation penetrates Martian soil, it produces oxidants such as hydrogen peroxide and superoxides. While toxic to most Earth life, Martian organisms may have evolved the ability to harness this energy. In a dormant state, they could survive for millions of years, becoming active only when conditions allow. NASA simulations of Martian environments show that certain Earth bacteria survived extreme radiation for 5 years. This proves that if life once existed on Mars, it may endure far harsher conditions than previously imagined. Another possibility is even more radical. Martian life may be fundamentally different from anything known on Earth. A research team at Cornell University proposed that in water-scarce environments, Martian organisms might use hydrogen peroxide as a biological solvent. All these hypotheses, from methane fluctuations to subsurface brines, point to one conclusion: Mars is not completely dead. It is a planet in transition, still breathing, still changing, and perhaps still harboring life. Every radar scan beneath polar ice, every drill into Martian soil brings humanity closer to the truth we have sought for over half a century. The search for life on Mars has progressed from skepticism after the Viking experiments to the most complex chemical evidence obtained by Perseverance. The final answer awaits completion of the Mars Sample Return mission, which will bring precious Martian samples